Hello, good evening, everyone. Today is the live session number 11. I'm assisting on the course of chemical crystallography, which has been taught by Professor Anshuman Rajodhari from IISA Mohali. Your exam is nearing, so I hope you all are following the course and you'll be ready for the exam by the deadline. So I'm the course TA. I'm Shani Varman from Department of Chemistry, IIT Hyderabad. I'm taking the live sessions on each Friday. So in this week, week number 11, Sir has taught us about mostly the powder X-ray diffractometer and how the powder X-ray diffraction works, and if there is how to detect and what is the disorders in the crystal structures and theoretical understanding about that, and how to treat disorders in the crystal structures by using the OLX2 software. So going to the problem solving sessions. So we are taking the questions from previous years. The first question is area detectors like CCD are used in X-ray diffractometer to measure only the intensity of the diffracted X-ray beam that hits the detector surface. So first we need to know what is CCD. So CCD is basically charge coupled device, which is being used as detector for single crystal X-ray diffractometers. So basically, what happens is CCD, the charge coupled devices have photosites or pixels. You must have heard the term pixels from your camera and all, or your on your phone also. So what happens during the single crystal X-ray data collection? The omega and phi angles change. We change the omega and phi angles with respect to the detector, like with the diffracted X crystal orientations, and then the data we are getting is a frame by frame recording of the diffracted X-ray beam intensity, and that data appears on the screen or the monitor. So what happens when light falls on the detector surface? It converts the light to charge and then charge to voltage. Now this voltage is amplified and recorded. Okay, so the answer for this question is true. We use CCD in X-ray diffractometers to measure the intensity of the diffracted X-ray beam that hits the detector surface. So it's true. Right? So it's true. Answer. Now the next one is the phase information cannot be obtained from mathematical relationships between the structure factors. Okay, so first we need to memorize what is the mathematical relationship. So for structure factor FHKL, we write as FHKL modulus plus the phase information, right? Now, uh, after getting the single crystal X-ray raw data, while we are reducing the data during the data reduction, we get the IHKL value, that is the diffracted beam intensity value for all the reflections we have collected. Now, what is the relation between the FHKL and IHKL? It is IHKL is proportional to the modulus square of the FHKL. Now, FHKL is structure factor only. But modulus FH scale, it is, I'll write here, amplitude of the structure factor. Okay, it's the amplitude of the structure factor. So the question is, the phase information cannot be obtained. You should be focused on cannot. Okay, cannot. So it can be, but you from here only you can see that phase information can be obtained between from the mathematical relationship between the structure factors, right? So it's true. Sorry, since it cannot be, so it's false. If it is written can be, then it should have been the answer that is true. The next one is the structure of small molecules may be solved even in the absence of phase information. So here from here you can see here we are getting the phase information. Now, if H scale, if H scale also corresponds to rho xyz, the density by Fourier transformation, right? Now, this rho xyz, this corresponds to the atom coordinates, corresponds to the atom coordinates located at different locations in the unit cell. Right. So as we use direct method to solve the structure, small molecules that those are the molecules having small unit cells like from so small molecules are basically having small unit cells. That is, volume can be 1 to 1.5 lakh Armstrong cube. So as we use direct methods, this for this small molecules, the absence of phase information can be neglected, right? And so and or uh, can be solved in the absence of phase information also. It's true. It's true. Now the next one is, if there is a center of symmetry, then the phases can be only 0 to 2 pi. No, it's wrong. It's from 0 to pi. So it's false. The next one is, which of the following does not pertain to the direct methods? Phases are chosen for a few strong reflections. Phases for other reflections are generated using phase relationships among strong reflections. This approach, the direct method approach, only works when data can be collected to high resolution, and the information about the unknown phases may be obtained by making a known change to the contents of the unit cell and measuring the effect on the diffraction pattern. The last one is the true one. Because from direct methods, which is a structure solving method for small molecules, then whatever information we get from that is about the unknown phases, right? Now, like it is obtained by making small changes in the raw data, like the unit cell parameters, the lattice parameters, and measuring the effect on the diffraction pattern. So this is the last option is the true one. The next one is, this following diagram represents two types of diffraction conditions A and B. What will be the scattered beam as captured in the detector for A and B? Now look carefully. For A, it is opposite phase, right? So it's destructive interference. And for B, it is same phase. It is constructive interference. So for A, it will be a dull spot. Dull spot, dull spot. Now for B, it should be a strong spot. B. So this is the answer. Okay. The next one is the sigma 1 relationship is applicable for Schonke structures, non-centrosymmetric structures, centrosymmetric structures. Always remember sigma 1 is for centrosymmetric structures. Okay. Now the next one is to match the following Patterson method, sigma 1 relation, triplet relation, and these are the three options given. You know, first of all, Patterson method is always for interatomic vectors. So 1b, 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 1b. Now sigma 1 relation. Sigma 1 relation is for centrosymmetric structures and it is used to get the info about the phase for reflection of 2H2K12 based on the phase of reflection of HKN. That is this one. So it's C. Now the left one is triplet relation should be the A, which is phases of EH, the normalized structure factors EH and EK are same, implies phases of E minus H minus K will also be the same. For triplet relation, you always know that the EK, and these values are always large. So the option will be 1B, 2C, 1B, 2C, 2C. Oh, these are the same options given. So you can just take any one. 1B, 2C, 2, 3A. The next one is if we have n atoms in the unit cell, then how many peaks will appear in a Patterson map? So basically, Patterson map is an interatomic vector map, right? To calculate these squares of the structure factor amplitude and a phase of 0. Now, each peak corresponds to the vector between the atoms in the crystal and the peak intensity tells about the electron densities of atoms. So if there are n atoms in the unit cell, then you will get n square peaks in the Patterson map. This is very important and you should always remember this. Now the next one is what will be the Patterson vector for crystal structures crystallizing in the space group of P21. Now it should be written like P21. So I'll be calculating according to this P21 screw. Right. So if you draw this stereographic projection, so you will get this is the screw axis, right? So if there is my first point, then P2, first twofold rotation, that is 180-degree rotation, it will come as here. Right. Now screw is like screw is basically rotation plus translation. Now it will go there and it will become here. So this will omit this. The same thing will happen in the four corners. You all know this is y-axis, this is x-axis. So this point will be x, y, z, and there will be another point here. So this point will be x bar, y plus half translation along y-axis, and z bar, x and z bar because of the 2, 4, right? So we'll write for the pattern how to get the calculate the Patterson vector. We write it like this: x, y, z, and x bar. For x bar, we'll write minus x, then y plus half, and then z minus for z bar. Similar, we'll write according like horizontally and both vertically. Minus x, y plus half, minus z. Now x, y, z minus x, y, z is 0, 0, 0. Now what if we minus x, minus 2x, y plus half, minus y, half, minus z, minus 2z. Next one is x minus of minus x, 2x, y minus of y minus half, z minus of minus z, 2z. This will be same 0, 0, 0. So if we take this 2, you will get the Patterson vector. It will be 2x half 2z. 2x half 2z, the first option. Yeah. The next one is which among the following is true for the unitary structure factor? Unitary structure factor is UH, right? So how to write UH? UH is equals to the modulus of UH, which is basically FH square divided by summation of the scattering factor from J equals to 1 to N. Right. So basically UH is directly proportional, the unitary structure factor is directly proportional to UH. This one is the option. Now its value ranges from 0 to 1 it should be. If it would have been written here 1, then this option will be correct one. The third option. Now the next one is which statement is true about the normalized structure factor EHKL? It is independent of cell dimensions, yes. It is independent of contents of unit cell, yes. But it is dependent on the presence or absence of inversion center, yes. So all of the above is the answer for the normalized structure factor. Now the next one is the value of mod of E square minus 1 for centrosymmetric and non-centrosymmetric structures. For centrosymmetric, it is 0.968. Where is it? This one. Yeah, 0.968, and for non-centrosymmetric, it's 0.736. This will be the answer to the second one. Next one is, if we have 6 atoms in a unit cell, how many vectors will Patterson map have? N square, right? 6 square equals to 36. So this is the option. Next one is, why do we need to normalize structure factor? So normalizing structure factor is important in X-ray crystallography to compare the intensities across different crystals, right? The structure factor F represents the amplitude and the phase information of the scattered waves from a crystal lattice, right? That we have already written before. F equals to amplitude of F plus phase information. Phase info. Now, normalization is necessary because this magnitude of the structure factor depends on factors like crystal size, sample thickness, number of unit cells, and right, crystal size, sample thickness, sample thickness, and number of unit cells. Number of unit cells in the crystal. So normalizing helps to remove these dependencies and provides a more intrinsic measure of the scattering strength. So by normalizing, you make the structure factor independent of the size and other experimental parameters that allows for a meaningful comparison between the different crystals or different experimental conditions. This is very crucial for like to accurately determine the electron density distribution within the crystal, which is essential for understanding the crystal structure. Okay, so the option will be because the reflections from different angles cannot be directly compared. So we need to normalize the structure factor, not to incorporate the information about the phase or not to normalize the intensities of all diffracted rays. The next one is unitary structure factor varies between 0 to 1. Just now I have told, yes, it's true. The next one is scattering factor F is equal to the atomic number Z when point atom is considered. Okay. So F is basically amplitude scattered by atom divided by amplitude scattered by the electrons. Right. So at scattering angle 0, at sin theta equals to 0, all the scattered waves are in phase. Hence, the scattered amplitude will be the sum of the contribution from all of the electrons present. That is the Z, the atomic number. So, F equals to Z when sin theta equals to 0. Hence, it can be considered as for point atoms. True. Next one is the phases for centrosymmetric structures are restricted between 0 to pi by 2. No, just earlier I have told is 0 to pi. So it's false. Patterson map is always centrosymmetric. Yes, it's always. So you may ask that why Patterson maps are always centrosymmetric. Yeah. So Patterson maps are centrosymmetric because Patterson map basically it's a mathematical representation to determine the relative atomic positions in the crystal, right? So it involves the autocorrelation of the electron density map of a crystal. Now the centrosymmetry in Patterson maps arises because the autocorrelation process involves squaring the electron density function, and squaring a function results in symmetric representation. This centrosymmetry simplifies the analysis of the map and aids in identifying peaks that correspond to the interatomic vectors. Right. So I'll just write Raster maps become centrosymmetric because it involves squaring of electron density functions and squaring a function results in a symmetric representation, right? So that's why. And this leads to interatomic vectors, which becomes essentially the Patterson map. Now, all the interatomic vectors in the Patterson map appear at origin? No. So, of course, false. I just showed you that this can be the vectors, right? So these are not necessary to be origin. Origin is 0, 0, 0, but this is not the 0, 0, 0. The next one is two polymorphs of a compound must have same conformation, same packing of molecules, different packing of molecules, same unit cell parameters but different space group. Yeah, different space group is true. And same conformation and same packing of molecules is not true, because if it is having, if both of them are having same conformation or same packing of molecules, then how they become two polymorphs? It will be the only one. So the third option is correct. Different packing of molecules are needed that leads to different space. Okay. And neither it has like both of them are having same initial parameters. Next one is polymorphs can be checked via which of the following? PXRD. PXRD basically we do PXRD, powder X-ray diffraction, to know about the phases, right? In which crystal system the compound belongs to. And IR we use to determine the functional groups, whichever functional groups are present in the molecule. So to detect the functional groups present in the molecule. Next one is single crystal XRD, and it gives us about the crystal structure, the bond angle, the torsion angle, the bond distances, etc. And UV. UV is basically absorbance. So if there are two different polymorphs, they will absorb in different wavelengths, and that will give you different peaks, and that's how you can distinguish between the polymorphs. Okay, so the answer is UV. The next one is how many maximum polymorphs can coexist in an equilibrium in an invariant system. It's three. You must have seen this type of structure. So these are the three polymorphs. Okay. The next one is iron can be used. Yeah. Iron can be used as a source of X-ray diffraction. Yeah, it's true. Actually, basically, uh, for X-ray diffraction, there is a need of X-ray, and it comes from a source, right? So source is basically the anode tube or the X-ray tube, and from like inside which you can employ any of the like metal, but it should have suitable resolution. Ultimately it should give suitable resolution. In that sense it should have suitable wavelengths of the energy. So basically x-ray source the choice of x-ray source depends upon various factors like the type of sample being studied, the desired resolution, or the experimental setup. So different elements are selected based on the characteristics of the X-rays they produce and how well those X-rays interact with the crystal structure. So iron is one of the many elements that can be used for the X-ray diffraction. So we just, if our sample is having, let's say, uh, the element, whatever element it is, if it is, if the electronic configuration or the electronic number configuration number is, let's say, n, then n minus 1 should not be used otherwise, because it might overbound with fluorescence, so or maybe it will create great background noise in the PXRD pattern. Otherwise any source can be used. Okay, these are all the questions I have collected from this year's assignment and last year's assignment. Now the week 11 assignment is already been given and uploaded in the portal, and the last date to submit the assignment is 11th October. Okay, please do submit your assignments. Okay, thank you. I would like to conclude the session now.